All right, welcome to episode 27. In this episode, I'm going to talk a bit about general thoughts on digital design for FPGAs and specifically an architecture for our display controller that we are trying to program into an FPGA. So there was a comment that a viewer left on my previous video that led me to a bit of a conceptual breakthrough that I think is going to enable me to get this project done. So I'll talk about that in a moment. So in addition to talking about these general FPGA design issues, I'm also going to cover some practical stuff. I'm going to clean up the Verilog code so that things are more modular. I'm going to show how to use a block RAM on an ICE40 device like the one we have on our Arduino 3 that we're using as our FPGA board. And most excitingly, I will implement a pixel line buffer that actually will output some varying pixel data on each line of output. And this is a good proof of concept that shows that our techniques for video generation should work. All right, so let's get started. All right, so let's talk about digital logic in an FPGA. And before we do, let me give you a disclaimer, which is to emphasize I am not an expert at this. I am at best an enthusiastic amateur, so please don't assume that anything I'm about to say is correct. If I do say something that is blatantly wrong, please do mention it in the comments, and this is an opportunity for all of us to learn something. All right, so here's how I view what is going on inside the FPGA. So basically we have a bunch of state, which I've drawn as though it's a single D flip-flop, but in reality it's a whole bunch of D flip-flops and also things like RAM devices. And this stores some information. On each clock cycle, we feed the current state that is in these flip-flops and memories into some combinational logic that transforms that data and sends it back into the state so that a next state can be computed and committed into the memory, basically the D flip-flops and RAM inside the FPGA. So basically on each clock, we take the current state, do a transformation using combinational logic, and then we get our next state. So to amend this a little bit, some of the information that comes into our state may actually be coming from input pins on the FPGA. Similarly, some of the current state data may be shunted out to output pins to control devices. So for example, the data that's being sent from the command FIFO is coming in on the input pins. And of course, our display output, the color information, the sync signals are getting sent to output pins. All right, so here is what I think is sort of the fundamental problem and the fundamental challenge of digital design for an FPGA, which is that this combinational logic essentially embodies all of the computation that we are doing in our design. It's taking our data, it's transforming it, it's adding, it's comparing, it's shifting, it's doing whatever operations we want to do on our data. And so the problem is the more complicated we make this combinational logic, the more likely it is that the propagation delays in the various gates and multiplexers and selectors and whatnot that are implemented here, the more that those propagation delays might be sufficiently slow that we don't actually produce a valid output in time to meet the deadline for latching that updated state into our state, our flip-flops and memory. And so in other words, the more we try to do in a single clock cycle, the more likely it is that we don't actually generate correct data to feed into our next state. And of course, anytime that we produce incorrect data that's then committed back into our flip-flops or memory, that means we've now generated an incorrect result. Our system is now in an incorrect state and it's not going to work correctly. All right, so the question is now, what do we do about this? How can we still get our FPGA-based design to do interesting things, given that we have to be really careful not to try to do too much in a single clock cycle? So the solution is pipelining, and the idea is that if you need to do a complex transformation of your data, rather than doing it all at once, you do it as a series of simpler transformations, and basically you can use registers or block RAMs as buffers to transfer data from one stage of the pipeline to another. So what really sort of crystallized my thinking about how to do this design was actually a comment by Jeremy X, which I'll put right here. And he had some very insightful comments about the problems that I had in my previous FPGA design that I showed in the previous video. So first of all, he asked, are you violating the maximum frequency of the FPGA? And as it turns out, I was clocking the global clock buffer at a frequency that was greater than what the datasheet recommended. And so since then, I have greatly reduced the frequency of the design. Originally, I was clocking it at 240 megahertz internally. Now I am clocking it at 80 megahertz internally. Also, Jeremy asked, I'm assuming the reason that you were going for a higher clock speed is to do the attribute palette and graphics lookups in between VGA pixel writes. And that's exactly right. I was assuming that my state machine would essentially do the various stages of processing all within a single loop, essentially driven by the core FPGA frequency. However, as we will see, pipelining does not require us to do these complex operations all at once or within the context of the same state machine. We can basically do them in parallel in different pipeline stages. As you can see, Jeremy commented, you could pipeline your design and get the same pixel throughput at 40 megahertz. I'm sure that's true. I'm going to use an 80 megahertz internal clock for now, so I get 2 clocks per pixel. It's probably adequate to just have 1 clock per pixel. But in any case, the pipelining, I think, is going to be the key to making this design work. All right, so here's a little graphical illustration showing the difference between a design that does not use pipelining and a design that does use pipelining. And so here, I'm assuming that to generate each pixel, we have 4 separate processing steps that need to be done, A, B, C, and D. So if we don't use pipelining, we need to do A, and then B, and then C, and then D, and then we output a pixel, and then we do A, and B, and C, and D for a different pixel, and output it, and so on and so forth. Basically, because all of these steps are done sequentially, we don't have a great deal of time to do each one. This more or less implies that we need a clock that is at least 4 times the pixel clock. And of course, the faster you drive the main clock frequency, the more likely it is that you're going to run into timing issues. All right, so here's a pipeline design. And once again, we're generating this green pixel, and then this orange pixel, and then this purple pixel. But the idea is we only need to do the very last stage of processing immediately before we output the pixel. The earlier stages of processing C, B, and A were done by different pipeline stages in the past on previous clock cycles. So basically, the data for one pixel sort of moves through the different pipeline stages. But what you can see is the advantage is that we are parallelizing our computation. So while the last stage of processing D is done for the green pixel, the second to last stage of processing C is done for the orange pixel, and the second stage of processing B is done for the purple pixel. And at any given time, all 4 pipeline stages are active, working on different pixels. And so the whole idea here is that we are starting the computation for each pixel earlier and giving it some time to move through the different pipeline stages. So the huge advantage here is that we can make our clock much slower and still do the same amount of processing for each pixel. So hopefully that does illustrate the advantage of pipelining. All right, so here is a possible design for our display controller. And before I explain how it works, let me first state what the goal is. So the goal is to have a 100 column by 37 row text mode. And I chose that configuration because if you have characters that are 8 pixels wide and 16 pixels high, then that is sort of the natural number of characters, rows and columns that you get when you use the 800 by 600 SVGA graphics mode. And I would like to be able to have an independent foreground and background color for each character that is displayed. So if you recall how the original IBM PC CGA text mode worked, where every character had independent foreground and background attributes, that's pretty much the same idea as what I'm going for. So there are 2 components. So the first component is this one that I've labeled fetch character and attribute data for next row. And the idea is based on what the next pixel row that we want to generate is, we're going to pull 1 row's worth of character and attribute data from the frame buffer. And so the frame buffer, I am thinking, is going to be stored in the SPRAM, single ported RAM in the FPGA. That is a relatively large block of memory, considerably larger than the block RAMs. And I think it is going to be the most natural place to put the character and attribute data. So as the character and attribute data is fetched, it's placed into a buffer, and we just have to have room to buffer 100 character and attribute values so that they can be communicated to the next stage. So I think we will actually have two buffers here rather than one. And so the idea is, as this component is placing one row's worth of character and attribute data into the buffer, a separate buffer is where the next pipeline stage is going to draw the character and attribute data from. So in other words, we can populate one row as the previous row is being consumed, and that way we're not getting into problems where this component might be writing data that this component is trying to read. So the second component here that I've labeled rendered pixel row, this is the component that actually takes the character and attribute data and turns it into a sequence of pixels, RGB color values that get sent to the display. So if our characters are 8 pixels wide, then for each character, we need to load 1 byte of data from the font associated with whatever character is being displayed. That will give us a sequence of 8 bits. Each one indicates whether a foreground or background color is displayed. And based on the attribute values, the foreground and background color values, we need to look up both of those in the palette data so that we know the correct RGB values, depending on whether we want to render a foreground or a background pixel. So in order to output the 8 pixels for the current row of whatever the next character being displayed is, we need to fetch some data. We need a couple of reads to fetch character and attribute data from this buffer. We are going to need one read to get the correct 8 bits for the pattern of foreground and background pixels to display from the font. And we are going to need a couple of fetches from the palette data to get the RGB values for the foreground and background color for whatever the next character being displayed is. However, we only need to grab this information once every 8 pixels. So there should be plenty of time to do this within the context of a single state machine. And the idea is we will sort of work on gathering the information we need for the next block of 8 pixels for the next character as we are actually sending the data for the current block of 8 pixels for the current character. So I'll note, this is still somewhat speculative. I'm not sure if this is exactly the design I will wind up going with, but I have thought about it a bit. I think this approach could work, so we'll see what happens. All right, so you'll notice that I've labeled some of these buffers, the font, the palette, this character and attribute buffer, as being BRAM for block RAM. So what exactly are these block RAMs? So let's take a look at what a block RAM is and how it works. All right, so here's a diagram of a block RAM for an ICE40 device. And so the UP5K device that the Arduino 3 has a total of 30 of these block RAMs, and they are 256 16-bit words. That's how they're organized. So there are 8 address bits that selects one of the words. So what is interesting about these block RAMs is that they are dual ported. There is a write port and an independent read port, and each side can be used at the same time. You can have one bit of logic writing data to the block RAM and a different bit of logic reading from the block RAM, and there are basically no issues at all in doing those simultaneously. So that's really what makes them useful for communication between components in your design. In terms of how you actually use one of these block RAMs in your design, it works pretty much like any static RAM. Let's say you want to write some data. You present the address on the address inputs, you present the data that you want to write on the data inputs, you assert the enable inputs. There are 2, they both have to be high, and then on the next positive edge of the write clock, the data that is on the data inputs gets stored in the internal RAM. Doing a read is similar. You present your address on the address inputs, you assert the enable inputs, they both need to be high, and then on a positive edge of the read clock, the data will be presented on the data outputs. All right, so just a few final things to note about these block RAMs. You can combine them, so if you need a wider memory or a deeper memory, or both, you can use multiple together. These are capable of reading and writing a data value on each clock cycle, so you can essentially stream data in and out of them at the FPGA's internal clock frequency. And finally, you'll notice that we have this mask value. That is basically used so that we can simulate narrower memories. So for example, you can, instead of organizing this as 256 16-bit words, you could actually make it 512 8-bit words if that's more convenient. All right, let's move on to the Verilog and we'll see how we can actually use a block RAM in our design. So one of the things I wanted to do in updating the Verilog was to modularize my code. It used to be that I did pretty much everything in a single file. I just had all of my always blocks that did all the various logic operations. They were all in the same code. I have split those out into modules. So here's the read command module. That is the state machine that reads data from the FIFO. I also split out the sync generation. So it turns out generating horizontal and vertical sync signals, it's pretty much the same logic. Really, the only difference is how the counters advance and when the state machines get updated. So these are now also a single module that's just instantiated twice, once for the horizontal sync and once for the vertical sync. So things are quite a bit more tidy now. So the most interesting update in this version of the design is that I am now instantiating a single instance of a block RAM. So I'm using the actual hardware primitive for a single block RAM, which on ICE40 devices is SB_RAM40_4K. So in theory, when you write Verilog, you're supposed to represent block RAMs as an array of registers that is accessed as though it is a RAM device, and then your synthesis tool figures out, oh, you want a block RAM, and I will instantiate block RAM for you and hook it up for you. I don't actually know Verilog well enough to know how I should structure my code so that that inference is possible. So instead I went with directly instantiating the hardware primitive. Eventually I'll probably will take advantage of the synthesis tool, but for now this does work. So all right, so what are we using this block RAM for? So right now all it's used for is to store an array of 16-bit values, each one of which is going to be treated as 16 pixels that are either a foreground or background color. So essentially what we're going to see is that if I can get data into this block RAM, and if I can get data out of the block RAM and feed it into the pixel generator, I'm going to produce on each line of output a pattern of foreground and background pixels, and the net effect is that we're going to see some vertical striped lines on our display that is generated based on the contents of this block RAM. And so all I am doing to get data into the block RAM at this point is I am taking the command bytes that I was using in the previous experiment to control the color of the pixels that were generated, the R, G, and B values, and instead I'm just going to directly put those command bytes into the block RAM. And so as we twiddle the potentiometers in the test circuit, we are going to see these vertical lines appear on the screen. Okay, so just for the sake of completeness, here is the state machine that actually processes bytes of data read from the command FIFO. And essentially, as each command byte arrives, we write it into the next word in the block RAM at sequentially increasing addresses. Basically, every time we complete a write, we increment the write address. And so as command bytes arrive, they get put into subsequent locations in the block RAM. The consumer side of the block RAM is, of course, the state machine that actually outputs the pixels to the display. And what sort of makes this interesting is that each word from the block RAM represents 16 pixels, but we always have to make sure that our 16 pixels are available at the exact time that we need them, meaning that we actually time things so that the reads from the block RAM occur ahead of when we actually need to generate the pixels. So this is sort of the game you play with FPGAs, is rather than doing a computation or grabbing data at the exact point you need it, it's better to do it ahead of time so it's already available at the point when you need it. All right, so here's our test setup. Right now, we're only displaying background pixels, so that's this blue color. But as I adjust these potentiometers, the Arduino is going to send commands through the FIFO to the FPGA, and basically those command bytes will get loaded into the block RAM where they will be rendered as foreground and background pixel color patterns. So essentially, when I start adjusting the potentiometers, what you'll see is that there will be stripes, vertical stripes that kind of go across the screen starting from the left, and there they are. Eventually we get to the point where the data values that are being stored are in the part of the block RAM that actually isn't being used to generate visible pixels, but if we send more commands, eventually we'll see new patterns on the left-hand side as the address wraps around, so there they go. So I have to say, the first time I saw this working, it was really exciting because essentially what it showed is that I can get data into the FPGA based on commands that are sent via the host interface, and I can use data that's in the FPGA to generate a non-trivial pixel pattern. So at this point, I am beginning to have an inkling of confidence that I think I may eventually be able to get this project to work. All right, so I think we've made some very good progress. We figured out how to use the block RAMs. We figured out that pipelining is going to be our organizational strategy. So there's still a ton to do. One big thing is I need to figure out how to use the SPRAM, which is the larger single-ported memory that we're going to use as the frame buffer. Also, now that we know that our command FIFO works, I think it's time to start working on some kind of command protocol where the host system can load character and attribute data into the frame buffer, can load palette data, font data, things like that. And of course, we need to implement the actual pixel rendering pipeline so we can actually see text, which is the whole point of the project. I'm also thinking of adding a second external FIFO, which the FPGA can use to actually send data back to the host system if the host system wants to read data from the frame buffer or one of the other internal memories in the FPGA. I think that will probably turn out to be useful. In any case, thanks a lot for watching, and I will see you in the next video.